Welcome to the next part of our lesson in Aqueous Solutions, Chapter 4. We are beginning lesson number 5, Concentrations of Solutions. So just to keep in mind where we're at, we're on the top of page 17 in our note packs. And this is now a calculator type of a question, so we will indeed be needing our calculators. So have one ready. This particular section we had covered very well in our first year of chemistry. So when I look at concentrations of solutions and introduce or remind us of a term called molarity, you're going to have a little bit of background knowledge as we begin this. So let me just kind of remind us a little bit of the algebra involved with molarity. When we use the term molarity, we're representing the concentration of a solution. Concentration simply means how much is dissolved, a given amount of solute in a certain amount of solvent. We reviewed the terms concentrated and dilute versus strong and weak. Concentrated and dilute, these two terms, let me get that written down, refer to the term molarity. Or there are other, certainly there are other ways to express concentration, but to a chemist the term molarity, which is abbreviated with a large capital M, refers to how much solute in a given amount of solvent. I could have a 12 molar HCl solution, which is very concentrated, 12 moles of HCl per liter of solution. I could have a 0.1 molar solution of HCl. This is very dilute compared to the 12 molar. I could have a 0.001 molar HCl solution, and now I can see that 0.001 is more dilute, 0.1 would be more concentrated, and 12 molar would be the most concentrated solution. So increasing concentration, looking at the term molarity. I wanted to remind us that we do know the word strong and we know the word weak. So what is the difference between how we define the term concentrated and dilute solutions compared to the term strong and weak? Strong and weak have to do with their electrolytic properties. How well do they ionize when placed into water? Strong electrolytes 100% break apart or dissociate or separate into their ions. Weak electrolytes only partially ionize or partially dissociate or partially separate as ions in solution. Strong and weak have to do with the degree of dissociation. How well do they conduct an electrical current in water? The weak, you remember, had the old double arrow to illustrate that we had an equilibrium process where reactants turn to products, but products go back to reactants. The dynamic equilibrium set up in a weak electrolyte. With strong electrolytes, we had just one arrow pointing to the right, 100% of the compound dissociated. Strong and weak, concentrated and dilute. We could have a very dilute solution of a strong electrolyte. HCl is one of our 7 strong acids that we memorized. We could have a very concentrated solution of a weak acid. Acetic acid or vinegar is a weak acid, and yet 12 molar is very concentrated. So I do want to just make sure we take a moment and reflect upon the distinction between the terms strong and weak, electrolytic values, concentrated and dilute. How much solute is actually dissolved in a given amount of quantity of solution. When we think about our definition of molarity, molarity we know is abbreviated as big M, molar units. It's moles of solute per liter of solution, moles per liter. Some of us like that algebra tool, the little helpful round little buddy, where we can place the term mole per liter to come up with the big M molar units. And this little trick says whatever the variable is that I'm looking for, I would cover it and I can find the algebra formula. If I wanted to know how to calculate moles, I cover it up. What's left? Liters times molarity. If I wanted to know molarity, moles over liter. If I wanted to know liters, mole over molarity, and so forth. So we're just looking at the round little buddy. Wouldn't hurt us to remember the algebraic formula for calculating a mole, where we take the mass measured in grams over the molar mass off of the periodic table. Grams over molar mass gives us a mole. So we can definitely put that into a round little buddy just to make it convenient. Mass measured in grams on the top, the term mole, and molar mass. How about if I just am allowed to abbreviate MM for molar mass or molecular mass, formula weight, sometimes you've heard me say. Now reflect upon the common unit found in both of these algebraic expressions. It's the term mole. To a chemist, we know the mole is the central calculation of all of chemistry. So if I'm looking at molarity times liter to pull out a mole, I can bring that down here, mole times molar mass to pull out a gram, and so forth. Let's just take an example and see what one of these problems might look like. Let's calculate the molarity. So we're looking for big M, molarity. I have a solution that contains 34.6 grams of sodium chloride, NaCl, and I'm going to dissolve that into 125 milliliters of solution. I'm looking for big M, molar units. To find big M, if this is indeed my target right here, big M, molar units, I need to know moles over liter. I'm given a unit of gram. I can do a little mole map work first, grams per molar mass to pull out a mole, and then moles over liters to find formula weight. So it's really a two-step process. Part one, let's use the mass measured in grams and the molar mass to pull out the mole. So step one of our problem, the mass measured in grams, 34.6 grams. I'm going to give myself a little more room here. I'll come down here. Here's the given, 34.6 grams of sodium chloride. And now my dimensional analysis uses conversion factors. I want gram to cancel, and I want to go into the mole. I know that 1 mole of sodium chloride, I'm going to add a 23 plus 35.5, which is 58.5 grams for the formula weight of sodium chloride. Hit that with me on your calculator. We'll take 34.6 and divide 58.5. And the number of moles is 0.5914. And I'll just leave that as moles of NaCl. Now what? Grams over molar mass got us to moles. We're ready to come up here and look at that second algebraic expression, moles per liter, to find molarity, moles per liter. So big M will be the second step of our two-part problem. Let's take that very value of moles we found, 0.5914, and place that over the liter of solution. Now recall, we must have that in a liter. They gave us a milliliter, so we simply slide the decimal 3 places to the left. 125 mLs becomes 0.125 liters. So here we have the moles per liter. So while that's on my calculator, I'll just leave that all in and go divided by 0.125. And we find a molarity of 4.73 molar units of sodium chloride. Number, label, unit. Should we try another? Example 2. Give myself some more room. Example 2. How many grams of HCl would be required to make 50 milliliters of 2.7 molar solution? We want to know grams. We're given the molarity and we're given the volume. Thinking about the very definition of molarity as moles per liter, If I want to figure out the number of moles, see what we're going to do? We're going to multiply liters times molarity. Finding the mole unit allows us to carry that down to our second round little buddy algebraic expression, take our mole times molar mass, and find a gram. So this time in our two-part problem, our solution will involve two calculations using the molarity formula first, and then bringing that down into the mole expression. So step 1. Let's solve for the number of moles. I'm going to take my 2.7 molar HCl solution, and I'm going to multiply it by the liters of solution. Molarity times liter pulls out the number of moles. Now remember the algebra, big M, moles per liter. I'm just simply cross-multiplying to pull out mole, but I've got to make sure that this is indeed in a liter. 50 mLs is 0.05 liters. So where are we at so far? 2.7 times 0.05 and is 0.135 moles. Step 2 of our two-part problem, let's solve for the grams. Solve for the mass measured in grams. And remember our round little buddy here, moles times molar mass pulls out the grams. We found the number of moles, 0.135 mole of HCl. Adding an H to a Cl gives us 36.5 grams per mole. That's our molar mass expression. So our old-fashioned mole map work. Mole times molar mass, and what do we find? 0.365, whoops, times 36.5. Let me repair that on my calculator. And I find 4.9275. Let's carry 3 sig figs, so 4.93 grams of HCl. Pause your video and talk to yourself. What were the steps that we just followed for number 1 and number 2? How are they alike and how are they different? And when you've taken a moment to process those questions, start the video back up. All right, you're back. Let's go on and try a third one. What would the concentration be if you used 27 grams of calcium chloride to make 500 mils of solution? I'm given a mass. I need to do some mole map work to find the word mole, and once I find the mole, I can put it into my molarity formula to find big M. We have 27 grams of calcium chloride. I want to convert that into a mole unit, so I find its molar mass. A Ca, which is 40, 2 of chlorines, which are 35.5 apiece. When I sum that molar mass, I come up with 111 grams as its formula weight. The number of moles is simply found by taking 27 divided by 111. And our mole unit here is 0.2432. If your screen is mine, it has all kinds of decimals. I'll stop there, of calcium chloride. Now that we know the moles, molarity can be solved by taking our number of moles just found above and dividing it by the liters of solution. So my 500 mLs put in as 0.5 liters, and I get a value of 0.486. We'll carry all 3 sig figs. Number label unit, and we have that accomplished. There's a little part under this question. What is the concentration of each ion? Well, this has a little to do with some stoichiometry, doesn't it? When calcium chloride dissociates, it indeed is a strong electrolyte. It's a water-soluble ionic salt, so a strong electrolyte 100% dissociates. We get calcium ions aqueous, and we get 2 chloride ions aqueous. Calcium chloride releases calcium and 2 chlorides. We know the concentration of our calcium chloride to be 0.486 molar units. The stoichiometric ratio, a 1:1:2 coefficient ratio. In calcium chloride, we would have the same number of calcium ions, so its concentration, 0.486, but notice how we get twice the number of chlorides released. So I'm going to double 0.486, and the resulting concentration, 0.973 molar units of our chloride concentration. Calcium chloride releases 1 calcium ion and twice the number of chlorides. Our concentration of chloride indeed would be twice that when compared to calcium. Let's read through number 4 and take yet another example. We'd like to calculate the concentration of a solution made by dissolving 45.6 grams of iron 3 sulfate. We're going to put that to 475 mLs of solution. We'd like to know the concentration, which is asking us to find molarity. So that's our target. What's the molarity? And then I see underneath that we'll talk about each ion as well. Let's begin by finding our mole value of our solute iron 3 sulfate. Given a mass, I need the formula weight, or the word molar mass, as my conversion factor. I need to add up the weight of 2 irons, 3 sulfurs, and 12 oxygens to find the molar mass of our compound. Iron is 55.8, and there's 2 of them. Sulfur is 32, and I count 3 of them in this formula. And oxygen has a weight of 16, and we said there are 12 of those. The sum of Fe2SO4 taken 3 times, I found it to be 399.6 grams in every 1 mole of iron 3 sulfate. Let's use that molar mass. Take my grams given to me in the problem, 45.6, divide by that formula weight we just found, and I have 0.114 moles of our compound. Now we can use that to find the molarity. Our number of moles we just found of our iron 3 sulfate per liter of solution. We had 475 mLs, so 0.475 liters. Moles per liter, 475, and I'm hitting that, and I find 0.240. And the unit there is big M, molarity of iron 3 sulfate. Now if we consider the next part of that and ask ourselves what would that make the concentration of each ion, it really has to do with just the stoichiometry. How many ions of each dissociate? In our compound, I'm noticing that there are 2 irons. And when they dissociate, they're going to release 2 units of an iron plus 3 charge aqueous ion. And here's the polyatomic ion called sulfate. There are 3 units of the polyatomic ion sulfate that carries a -2 charge. My ions have charges. We determined the concentration of the iron 3 sulfate compound to be 0.240 molar. We're being asked to calculate the concentrations of each of those ions. Well, I can clearly see 2 iron ions will be released, so it would be twice the value of 0.240. 0.240 doubled is 0.480 molar units of the iron ion, and 0.24 times 3 is 0.72 molar units of your sulfate polyatomic ion. 3 times the value for sulfate, 2 times the value of iron when compared to the compound of iron 3 sulfate. We're going to turn our page, top of page 18, and we'll find our next example, example 5. This is a little bit more involved simply because I have to use words. It's asking me to describe. Describe how to make 100 milliliters of a 1 molar potassium chromate solution, K2Cr2, you know what, that needs to be 07. Can you make that correction on your page 18? Potassium dichromate. I have a subscript error. K2Cr2O7, which will indeed change our molar mass and so forth. So let's agree upon the correction to make the top of page 18 read K2Cr2O7. I want to know how to make that. Well, keep in mind that any type of ionic compound, I'm going to end up needing to know how much of this to weigh out. So what I'm looking for truly is my gram. I have a 1 molar solution of potassium dichromate. I'm going to multiply that now by my liter unit. 100 mLs is 0.1 liter. And what this is going to allow me to calculate is the number of moles of my solute potassium dichromate. So let's hit that first. 1 times 0.1 is 0.1 mole. We don't go to the scale and weigh things in moles. We go to the scale and weigh things in grams. So I have a little mole map work to make sense of this. My 0.1 mole of my salt, ionic salt called potassium dichromate, needs to convert into a measuring unit known as mass in grams. So I need to know the molar mass by adding 2 potassiums, 2 chromates, and 7 oxygens. Let's do that. Potassium first has a formula weight of 39, and there's 2 of them. Cr chromium, atomic weight of 52, and there's 2 of those. Plus oxygen's mass of 16, but I'm counting 7 of those in the formula. The molar mass I found, 294 grams. Mole times molar mass, and the grams that I found would be 29.4, and let's record that. Now at this point, I have a mathematical answer, but I haven't truly answered the question because it wanted to know describe. And to me, I will not give credit unless I actually describe. So let's do that. Let's give a description or a simple set of directions of telling a student what to do to make this desired solution. First thing our student would have to do is to weigh out, using a scale, weigh out exactly 29.4 grams of your salt, a solid ionic compound called potassium dichromate. Weigh it out. You're going to add 100, I had to go back and look, add 100 milliliters of water. and some type of container. I'm sure you're going to use a beaker to make your solution. So after you weigh it out, you probably want to put it into a beaker. You'll add the 100 mils of water, and it's always a good idea to remind that student to stir to make it indeed a homogeneous solution. You don't want to see any bottom part, any type of salt still sitting at the bottom. So stir until it's uniformly dissolved. We have one more in this set. Let's take a peek and wrap up this example. Number 6. How do I make 250 mils of a 2 molar copper 2 sulfate dihydrate? Copper 2 sulfate dihydrate. Now this, my friends, reminds us of an experience back in first year chemistry using a hydrated crystal. When we talk about a hydrated crystal, we use this little dot in the formula to say attached to, not to multiply, but attached as part of its compound. Inside this little crystal lattice structure is some water molecule trapped. We once conducted an experiment that masked the amount of water contained in copper 2 sulfate. We heated this blue hydrated crystal. We heated it strongly over a flame until it turned white. We turned it into an anhydrous form. Weighing it before and after the heating allowed us to calculate the amount of water that indeed was contained in the hydrate. So here, this little dot, dihydrate, means there's 2 water molecules attached to the copper sulfate. The reason I'm stressing this is the water plays a role in the molar mass when we calculate moles. So let's do our unit of molarity. 2 molar copper 2 sulfate dihydrate times the volume, but in a liter, and we'll pull out the number of moles of our solute. 2 times 0.25 is 0.5 moles. That 0.5 mole of our copper 2 sulfate dihydrate. Now see, we need the molar mass, don't we, to figure out the gram. How many grams does 1 mole of copper 2 sulfate dihydrate weigh? Alrighty, so we have a little mole map work to do here. Let's take a moment and kind of sum CuSO4. Now copper 2 sulfate, copper is 63.5 plus the sulfur at 32 plus 16 times 4. I get this particular part of the compound. That molar mass is 159.5, but there are water units as well. There's 2 of them. So I have 2 waters. 2 H's and an O is 18, the molar mass of water 18, but I need to double that because there's 2 moles worth. So that's 36, isn't it? 2 units of water adds to 36. So let's sum the whole critter and we get 159.5 plus 36. This molar mass altogether 195.5 grams. And that's what will get used up here as my conversion factor for copper 2 sulfate dihydrate. We have to include the water in that formula weight. Multiply that molar mass by 0.5 and we're finding an answer of 97.75 grams of our copper 2 sulfate dihydrated crystal. Remember, it said describe, so I have to use words without the sentence or without some sort of step-by-step instruction for a student. We have to describe, tell the student what to do to make this solution up. So let's start by using a verb, shall we? Let's use measure or weigh out 97.75 grams of your copper 2 sulfate dihydrated crystal. We will measure How much water did it say? 250 mLs, 250 mLs of water with a graduated cylinder. So this is just a little bit different than what I set up above, a little bit more descriptive. Combine the two in a beaker. And oh, so important to stir until it's uniformly dissolved, creating a homogeneous solution. This is a good place to pause, reflecting upon the lesson so far, how to use molarity, liters, molar mass, and mass measured in grams to convert from one unit to any of the others. When you are ready, you're going to start the next part of your lesson, and we'll talk about dilutions. How do I take a more concentrated solution and dilute it to a desired concentration? MV equal MV. In the next part of our lesson on molarity, we'll talk about the process of making a dilution. To dilute a solution simply means to add more solvent, which is typically the water, adding more water to a known solution. So taking its concentration and lessening it by adding water. Now remember that molarity times liter always gives us this unit called the mole unit. The number of moles, MV, is equal to the number of moles, MV. See, just because I add more water to a solution does not change the original content of the salt that we added. So let's suppose I have this little beaker of water here and I just sprinkle in some sodium chloride. So here's little sodium chloride crystals at the bottom, stir, 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 and it dissolves. Well, I can increase the volume of the water, diluting the solution, but I have not changed the number of moles of the original solute. So mole equal mole, MV equal MV, will be our formula for calculating how concentrated a solution is, how dilute a solution is, and how much water would we need to add to create a desired concentration. Another term that I will be using is called a stock solution. It's a solution of known concentration. It's typically what's sitting on your shelf in the chemical stock room. We use this to make a more dilute solution. So it's the starting solution. What do you have on hand and how much of it do you need to create the desired quantity of a concentration that your lab calls for? So let's just dive in and take a quick peek at how easy these particular problems are. We'll do a little practice problem. It's number 7 in your note pack. We'd like to know the volume of a 1.7 molar solution needed to make 250 mils of a 0.5 molar solution. Reading through that problem, I'm given molarity and volume pieces of information for MV equal MV. Our first molarity of 1.7 molar times our target variable V1. How much of 1.7 molar? So those two go together. And the MV2 over here is 0.5 molar and its quantity of 250 mLs. Now friends, notice with this algebra, it is absolutely okay to leave this in a milliliter. Leave it in a milliliter and you'll get out a milliliter. So we'll hit V1 by simply taking 0.5 times 250 and divide that by 1.7. And let's hit that and see what we find. Our answer will come out in a milliliter. 0.5 times 250 divided by 1.7. And we find 73.53 milliliters. And it did not give us an identity of that solute, so we can't identify. So just a number and unit would be appropriate here. Should we try another? Let's read through 8 together. We have 18.5 milliliters of a 2.3 molar HCl added to 250 mils of water. What is the concentration of our solution? We have 18.5 mLs of a 2.3 molar HCl solution. Now, as I'm reading this carefully, read it with me, is added to 250 mils of water. So 250 mils is sitting in there. We add 18.5 mils of the solution, so the new combined volume must be the V2. I'm going to write that out so you see the difference here. Up above in that first question, our target, the entire solution ended at 250 mLs, but here's worded just a little different. I take 18.5, add it to 250. Well, there's the add it to 250. We need that combined volume component there. And we want to know the resulting concentration, so we're going to be looking for the concentration unit of molarity. So 250 plus 18.5, that 268.5, that becomes the V2 in our formula. So let's calculate for M2. We start on the side without the variable. We get 18.5 times 2.3 divided by that combined volume of 268.5, and the new resulting concentration, 0.158 molar. And this indeed give us the unit here and label HCl. Let's read through another. Number 9. 18.5 mLs of 2.3 molar HCl is diluted to 250 mils with water. What's the concentration? We have 18.5 mLs of a 2.3 molar diluted to 250 mils. What's the resulting concentration? And I really want you to take care of 8 and 9. They are so similar, but oh so different. The difference here, the word in number 9 does not say added to. It says diluted to. This is the total volume. They're not being added together. It says you're going to add water. So I have 18.5 mils to begin with. I just add water up to the 250 mil mark. I didn't add 250 to the 18.5 as we did in number 8. So just a slight difference in the wording of that problem, but see how important it is to be a careful reader. Number 8, we had to add the volumes. Here we do not. So let's do the algebra. 18.5 times 2.3 divide by 250. And now our resulting concentration, a little bit more concentrated, 0.1702, so about 1.170 molar HCl. One more in this set. We'll finish this lesson. You have a 4 molar stock solution. Describe, that means words, how to make 1 liter of 0.75 molar solution. Well, our stock solution is 4 molar. How much will we need to measure out to create a desired amount, 1 liter, and it should end up to be 0.75 molar units for its concentration. Start on the side without the variable, so 1 times 0.75, you'll divide out 4, and V1, 0.1875 liters. Now I'm not done because the words here describe. Let's measure 1.875 liters is 187.5 milliliters, and I like that because that's what our graduated cylinders actually measure in as mL. So the little marks on the graduated cylinder are matching the unit here now. Measure out 187.5 mils of your 4 molar stock solution using a graduated cylinder. So into the cylinder, pouring from the stock bottle 187.5 mils, and then stop. Now what? add water up to the 1,000 mLs. That's what a liter is 1,000 milliliter. You can certainly leave these in liters. You just want to be sure you have some common units here. And it's always good advice to tell them to stir to create that homogeneous solution, all mixed evenly throughout. Stir it up, shake it up, make sure it's uniform. And now we have described how to make the desired solution from our stock bottle. You have now completed your lesson 5 on molarity. You have enough information to practice now your assignment number 5.